Okay, so this is the full section of the vectors chapter, Core 1 book, and this is calculating the angles between lines and planes. Now if I want to calculate the angle between a line and a plane, or between two lines, so I'll draw two, say, intersecting lines like this, and this arrow represents the direction it's going in, and let's say that this is a vector A, this is a vector B. Now these vectors will come from, let's say if it's a line, so R equals A plus lambda B. Okay, well actually now let's call this, no, we'll leave it like that. So that B is what we use here, so that's the direction part of the line. So if I've got a different line here, let's call it R2, A plus lambda B, then this vector that we use here is what we'll call the direction vector. Okay, so in this R equals A plus lambda B, okay, the vector B is the direction vector of the line, which we use in this formula here. So this formula, because of the modulus sign, will give us the acute angle between two vectors or two lines. So A and B, these are going to be the direction vectors of the lines. So at the top you can see that we need to do A dot B, so we're doing a dot product, which we've been introduced to before, and here we want the length of A times by the length of B, and we can use this to work out the acute angle between the two lines, but we must make sure, as it is in this diagram, that the vectors are pointing away from the angle that we're trying to find. So in this case it will probably be this angle here that we're trying to find, that acute angle. Now if I want to find the angle between a line and a plane, so I'll try and draw out a plane. So imagine that this is some sort of 2D flat area, and I've got a line like this, okay, and what I want to do is to work out this angle here between that line and the plane, and the formula we use for that is sine theta equals, so it's very similar to the previous one, it's B dot N over the length of B, vector B, times by the length of vector N. Here the vector B is going to be the direction of the line, the direction vector of the line, just like before, direction vector of line, and N represents a normal of the plane. Okay, in other words, a vector that's sticking up perpendicularly from the plane. So if it's the angle between two lines, we want the vector, or we want the direction vector of the line. If it's an angle between a plane and a line, what we want is the direction of the line and a normal in the plane. Okay, so we've got these two lines. So this is the line L1, this is the line L2. We need the direction vectors of both lines. So here's the direction vector of L1, here's the direction vector of L2. That's what I'm going to use in my calculation. So if I call A the direction vector of L1, this 3, -8, -1, so this is the direction vector of L1, and B, if I call that the other one, which is 2, 2, 3, written as a column, this is the direction vector of L2, and because I'm finding the acute angle between them, these need to go into this formula, A dot B over length of A times the length of B, and then I want to find the modulus of all of that to make it positive, to make sure that I get an angle between 0 and 90 degrees, so that I get a this acute angle. So let's start with A dot B. So A dot B, that's going to be 3, negative 8, negative 1, dot 2, 2, 3. So that's 3 times 2 plus negative 8 times by 2 plus negative 1 times by 3. It's going to be 6 minus 16 minus 3, which I believe is going to give me negative 13, so minus 13. Then I also need to work out the length of A. So that's just doing Pythagoras on the 3, the negative 8, and the negative 1. So that's going to be the square root of 9 plus 64 plus 1. So that's root 74. And then I want the length of B. So that's just doing Pythagoras on the other vector, the 2, the 2 and the 3. So 2 squared plus 2 squared plus 3 squared. So that's going to be the square root of 4 plus 4 plus 9. So that's root 17. So now I've got everything I need to go into the formula. So I've got my A dot B, which is going to go at the top. These two are going to go at the bottom. They're going to get multiplied by each other, and that will give me the cosine of the angle. So I want the cosine of the angle is going to be the modulus of negative 13 over the root of 74 times by the root of 17. Now, because I've got a modulus sign, that whole fraction effectively becomes positive. Yeah. So I'll just write down that I'll do work out 13. Actually, what I could do now is just work out theta straight away, rather than work out decimals and things. I'll put theta. That's going to be the cos inverse of 13 over this root 74 root 17. So let's just type that in and get theta. Save a bit of time. So cos inverse fraction 13, because the modulus has made it positive, root 74 times by root 17. Okay, and that gives me 68.4985. We want the answer to one decimal place, so that'd be 68.5 degrees. Okay, so we've got a plane that passes through a point and is perpendicular to the vector n. Given that OA equals this, okay, so this is a point on the plane, or a point in the plane, a point in the plane. And this vector here, which is perpendicular to the plane, okay, this is a normal to the plane, because normal, it means perpendicular, normal to the plane. Okay, and you can see like a little diagram here. So there's our normal to the plane, and this represents a point in the plane. And if I want to find the vector equation of a line, so vector equation of a line, of a plane, and you'll notice here this pi, yeah, and we can't often use that's an uppercase pi used for planes. So quite often when we're doing questions and we're talking about planes, you'll often see this uppercase pi used. So anyway, the vector equation of a plane is r dot n, so that's the normal in the plane, equals a dot n. Okay, so A is going to be a point in the plane. So I'll put where A equals point in the plane, point in the plane, and N equals a normal to the plane, In other words, a vector which is perpendicular to the plane. So in part A, so we've got r dot n equals a dot n. So we just substitute these in. So r normal to the plane, n, let's write it in this form. Well, we've got it already, haven't we? In column form. So all I'm going to do now is substitute them in. So that will be r dot, so our normal is 3, 1, negative 1, equals, our point in the plane is 2, 3, negative 5, dot with the normal, which is 3, 1, negative 1. So the left hand side remains the same, 3, 1, negative 1. Now we work out the dot product on the other side. So if we do the dot product of that, we'll get 2 times 3 plus 3 times 1 plus negative 5 times by negative 1. So that would be 6 plus 3 plus 5, which will be 14. So actually our vector equation for the line is just going to be this. We just put equal to 14. So here's our answer to part A. That will do. Now we could, if we wanted to, we could write this vector as 3i plus j minus k. That's an alternative way of doing it. Now if I want to write the equation of the plane now in Cartesian form, part B, okay, all we do is we replace r with the vector x, y, z. Okay, so to write the equation of the plane in Cartesian form, replace r with the column vector x, y, z. So that's all we do, and then we do the dot product and see what we end up with. So I'll have, instead of r dot 3, 1, negative 1, I'll have x, y, z dot 3, 1, negative 1 equals 14, and that's easy now. Do the dot product on the left hand side, 3x plus y minus z equals 14. So there's my answer to part B. Very quick and easy to actually convert the scalar or vector form into the Cartesian form. Now just a reminder, if I want to find the angle, the acute angle between a line and a plane, it's this formula. So sine, the sine of the angle is equal to b dot n, and I'll just remind you what b and n are, over the length of b, vector b, times by the length of vector n. Now b, that will be the direction vector of line, direction vector of the line, and n will be a normal to the plane, yeah, or a vector which is perpendicular to the plane. So we're going to look at what we've got here and pick out B and N. So this is the direction vector of the line, so that is going to be my vector B in the equation. So I'll just put B equals, let's do it as a column, 3, 4, negative 12, and N is going to be the normal to the plane, okay, and that's the vector 2, negative 2, negative 1, because remember what we've got here, we have got the equation of the plane written in the form r dot n equals a dot n. So you can see right next to r we have that vector which is a normal to the plane. Now everything can just be plugged in. Well, I suppose the first thing is we'll work out the dot product and the length. So B dot n is going to equal, so that's 3, 4, negative 12 dot 2, negative 2, negative 1. So that will be 3 times 2 plus 4 times negative 2 plus negative 12 times by negative 1. So it's going to be 6 minus 8 plus 12, which is 10. And then I want the length of B, so I just do Pythagoras on the three numbers 3, 4 and negative 12. So that's going to be the square root of 9 plus 16 plus 144. So let's see that, 9 plus 16 plus 144. 9 plus 16 plus 144. Okay, so that's actually the square root of 169, which is going to be 13. And then the length of this normal is going to be Pythagoras on 2, negative 2 and negative 1. So that's going to be the square root of 4 plus 4 plus 1. So that's going to be a square root of 9, which is 3. That's nice. So we get some nice numbers. So we have our B dot n, which is going to go in the top. And we've got the length of B and the length of n. So now they can go straight into the formula. So the sine of the angle is going to be the modulus of B dot n, which is 10, over 13 times 3. Now we're working out the modulus of this, but it's positive anyway. So that means that the angle is going to be the sine inverse of 10 over 13 times 3, 39. So let's work that out. It doesn't say how many decimal places, so I wonder if we get a nice number or not. 10 divided by 39. Okay, so yeah, we're going to have to round this because we get 14.85, whoops, 7, and it carries on. 3 significant figures, so theta equals 14.9 degrees. So remember, if nothing is specified, we round to 3 significant figures. Okay, so in this example here, it says find the acute angle between two planes, and we're given the vector equation of two planes. So again, the equations of these planes are given in the form r dot n, where n is this vector which is perpendicular to the plane or normal to the plane, a dot n. Okay, and that a dot n just becomes a number. And here we have the formula that allows us to work out the acute angle between two planes. Now again, can you see it looks very similar to the other formulas we have, but the two vectors we have, n1 and n2, are these two normals. So the first thing we need to do is to write down what is n1, what is n2. So n1 is going to be the normal to the first plane, which is 4, 4, negative 7, and n2, that's going to be the normal to the second plane, which is 7, negative 4, 4. So I'm now going to work out n1 dot n2, so the dot or scalar product of these two vectors of 4, 4, negative 7 dot 7, negative 4, 4. So that's going to be 4 times 7 plus 4 times by negative 4 plus negative 7 times by 4. So that's going to give 28 minus 16 minus 28. So that just gives negative 16. Then we want the length of vector n1, which is going to be Pythagoras on 4, 4, and negative 7. Okay, so that's going to be square root of 16 plus 16 plus 49. So that's 32 plus 49, which gives 81. Square root of 81, well, that's just 9, that's nice. And then the length of n2, Pythagoras on 7, negative 4, and negative 4. Actually, it's going to be the same as the last one, isn't it? Yeah, because you basically got 49, 16, and 16. So these two normals are the same length, even though they go in different directions. So you've got 49 plus 16 plus 16. So again, that's the square root of 81, which is 9. So now we plug that into the formula. So the cosine of the angle, the modulus will make it acute. It's going to be n1 dot n2, which is negative 16, over basically 9 times 9, isn't it? That means that the angle, the acute angle, is going to be the cos inverse of 16 over 81. So let's see what that gives us for theta. So remember, the modulus has made it positive. And that gives us 78.607 degrees. We want a final answer. If it doesn't say anything, we go for 3 significant figures. So 78.6 degrees for the angle between these two planes. Right, you should now be able to do exercise 9D on pages 187 to 189. So there's a recap here of all the different things that we have. So we've got up here, this is how we find the angle, the acute angle between two lines. If I want to find the acute angle between a line and a plane, I use this. So line and plane. If I want to find the acute angle between two planes, I use this formula. All we need to know is that when it's a line and it's in this form, or whatever scalar it is, this is the vector that I use for the direction vector, which goes into one of these formulae that we're going to use. And for a plane, when it's written in this form like this, then this is the vector I'm going to use here for the direction vector that goes into the formula. And I suppose it does give the direction of a plane, but like the perpendicular direction of a plane. So that's what we use it for. And if I need to convert the vector equation of a plane into Cartesian equation, then all I do is I take this, I replace it with the vector x, y, z, and basically then work out what the dot product is with the vector n that I have here. So we'll have some numbers here, and that will equal some sort of number over here, and that will convert the scalar or vector form of an equation into Cartesian form.